So with our data now prepared, let's start the process of modeling the data, but of course we always want to plot what's going on with our data before we actually build any model. The basic plot that we would do then looks something like this, but if I plot just the missing number of elements as a function of location, it gives me a box plot, and that's fine. We can see some of what's going on here. And the nice thing is that the plot function in R does this by default when you've got factors for location, and it understands them as such. But as I've said before in the plotting tutorial, with these sorts of box plots, you can't really see a lot of what's going on. And so I prefer to actually kind of make location numeric. If I run as numeric on location, right, it takes that and interprets location not as a factor but as numbers 1, 2, and 3 instead of factors like AK, OH, and JP or whatever we've got. What we then run into, though, is that, as you can see in the plot, there's a lot of points that are plotted on top of each other. This is a common thing with discrete data of any kind because you've got a bunch of zeros, 1s, 2s, 3s, and 4s in the data, and they're all being plotted on top of each other. So we can use that jittering trick that we did before, where if we add the jitter function to our x-axis when we plot, it adds a little bit of random noise and spreads these out a little bit, so we can see that, wow, there are a lot of zeros and kind of fewer and fewer counts as we get higher on the missing number axis. So this is what our data looks like. This is what we're going to model. We're going to model the missing number of elements on the y-axis here as a function of location, these 3 different locations. And so to do that, right, what we've got to do is make a GLM. So let's call it missing GLM, since that's our response variable. Use the GLM function as we did before. Missing as a function of location, data equals gold sub. And now, as before, right, GLMs take this extra argument called family. With the family argument, we need to specify the probability distribution that's going to best describe our errors, our residuals. In this case, because we're dealing with count data, right, that's going to be what's called a Poisson distribution. You'll recall from the lecture on probability distributions and from what I've said previously that Poisson distributions are really quite good at describing count data that are discrete integers that are bounded by 0, range from 0 to positive infinity, but no decimal places. And so we want our residuals here in this GLM to be distributed according to a Poisson distribution. That's the stochastic part of the model, right? And then we also want to specify the link argument. In this case, link equals log. And we're doing this, once again, because our data are bounded by 0, and they can only take positive values. And when you take the log of 0, you get negative infinity, right? So we can then transform our positive values onto a negative infinity to positive infinity scale, and in doing so, allow it to be modeled kind of as we normally would with a linear model. And so this GLM function here that I've just run to create this missing GLM object, this is a Poisson family generalized linear model with a log link function. And now the log link function is actually the default for the Poisson, so what you could also do is just not even include that, and if you run the model this way, it still will have a log link, because that's kind of the default when you specify Poisson. It's kind of good at practice to keep it in there, though, so that you know what you're doing, and you can see it and other people can see it too. Now, let's... as we've always done before, right, we inspect the diagnostic plots of the model, right? We would plot our model object. But as I started to hint at with the log normal GLM that we made, Once you get into GLM territory, these diagnostic plots become less useful, right? If I were to run this and start pulling up the plots, right? Take a look at this first plot, the residuals for each of the categories. Obviously, there's a lot of residuals plotted on top of each other here, right? And you can see that these residuals are really not normally distributed, it looks like. There's a bunch of values on top of the model fit line, but not a lot underneath it, even though there are lots of zeros there. But more importantly than that spread is just the fact that these are not continuously distributed residuals, right? These are discrete values of the residuals, and so there's very clearly a violation of kind of normal distribution going on here. We can also see that the residuals seem to be spread somewhat evenly across there, but again, with a Poisson distribution and count data, as I said, count data are probably not homoscedastic. We expect heteroscedasticity with count data and Poisson distributions. And so that assumption really doesn't matter anymore for a GLM. So again, this residual plot really isn't telling us much like it was before. It can tell us if we might have non-independent errors, perhaps, or if we've got a non-linear fit, but so does just looking at the model fit plotted. So these diagnostic plots become less useful, right? The QQ plot here, obviously, as I've said before, these data are not normally distributed, so why would we expect it to fall along that dashed line in the QQ plot? And you can see that there are all these kind of horizontal rows of points, definitely not normal, and we're deviating from that dotted line anyway. But again, it doesn't matter if it's not normal because we know it's not, and we're saying it's not by saying family equals Poisson. So these diagnostic plots really only matter for LM objects, not really for GLM functions. This one is kind of interesting because, as I said, we expect heteroscedasticity. So this red line should be going up, and it is, but not all that much. So we've got actually quite a good degree of homoscedasticity here when we don't expect that to be the case. But again, this doesn't really matter that much because we're telling the model that we're expecting heteroscedasticity here. And we can see kind of one of the confidence intervals for Cook's distance, no really undue influence of any outlier here. And so that's all well and good. But so these diagnostic plots, as I said, really matter more for linear models than for GLMs. They're not really telling us all of that, any particularly useful information when we get into the world of GLMs.